Hello to all. Good morning. So welcome to this tutorial 3, which is being given by Jonu George from Nutanix and Amit Saha from Cisco. It's on end-to-end machine learning using Kubeflow. I think these days it's all about deep models and end-to-end machine learning. So um, I think this tutorial is all about how you can use Kubeflow for end-to-end machine learning. So I'll just pass it over to the presenters without much ado. Thank you. Over to you, presenters.
Hi, good morning, everybody. And I guess for some people, it's good evening, good night, wherever you might be attending this from. I'm Amit, and along with me is my co-presenter, Jonu. I'm from Cisco, Jonu is from Nutanix, and we have been actively working on an open source project called Kubeflow for quite some time, which is all what this tutorial is all about. So I will jump right into the presentation, and the way we are going to do this is that I will first present the some slides where we give an overview of the entire project and what we are going to what are the most important things according to us about the project, and that should take us around 30 minutes. Post that, we will have any we'll pause for any questions that we might see on the chat. Following which, Jonu will take over and he will show some actual runs on AWS, and show the basically a demo of most of the things that we'll talk about, right? And after that, again, we'll have some question and answers, right? We are trying to we plan to finish everything within the stipulated 1.5 hours. And so if I'm sometimes going too fast or things are too fast, then please raise your hand and we can slow down a little bit. Okay? So I will now start presenting my slides. So give me just a second.
Before that, Amit, so anybody who has questions, you can put them on the Q&A tab. There's a Q&A tab that you can see on the top right of your screen. At least that's how it is for me. There's also a chat tab where you can put your questions. So either way, so you can have the questions both ways. Thank you.
Okay, thank you. So I am trying to switch to my presentation, and it should be live anytime soon. Yeah. The presentation is visible now, right?
Yes.
Okay. Okay. So the title of this tutorial is End-to-End Machine Learning Using Kubeflow, and as I said, our presenters are myself, Amit, and John. So this community is pretty used to machine learning projects, and I'm pretty sure most of you also know that ML science projects are pretty cute in the sense that it's very easy these days to just like download a piece of ML code from anywhere on the internet and start running it, and within a day or two you will have some sort of functional stuff doing what you want to do. Accuracy and how good the models are, that's a different issue. That's a more engineering issue and needs a lot of runs, but to get something up and running is pretty easy, right? But just as in the herd, a calf doesn't survive in the wild without the herd. An ML science project doesn't survive by itself. So many a times we'll see the projects are done and then they are shown in some demo or some proof of concept, and that's kind of the end of the project, right? It never sees the light of day. And when I say the light of day, it means it never reaches a stage where it can be it can, if not by itself a product, it can be part of a product. So the main reason behind this is that usually the concept or the perception is that this machine learning code is the elephant in the room, and that's the biggest and toughest problem to solve, right? Whereas all these peripheral things such as data verification, resource management of where you are running your machine learning code, the serving infrastructure, monitoring, all this kind of stuff, um, uh, feature extraction, configuration, all this kind of peripheral stuff are given much less importance, right? And so all the focus goes to the ML code. and whereas the reality is way different than what the perception is, right? The ML code actually is a pretty simple piece of code. I'm not arguing against the complexity of the ML algorithms as such, but once something is defined, once the algorithm is known, and we can, as I said, pretty much download a piece of ML code and test and tune it on your own laptop and get it to a stage which can do a proof of concept, right? But this all this other peripheral stuff now become the kind of elephants in the room and become the bigger problems when you want to make this into a production grade piece of software, right? Or being used in a production grade piece of software. So uh, in other words, there is something which we commonly use in software engineering, which is the concept of DevOps, and DevOps becomes very important when you want to make something practical and use in production setups. So some real life examples of how things go. This is a little bit dated, but even then, the story of enterprise machine learning. It took me 3 weeks to develop the model. It's been more than 11 months, and it's still not deployed. And this is pretty much common, and I'm pretty sure many of you might have had a lot of projects, which not necessarily all of them were targeted for production or for deployment, but you could possibly understand how difficult it becomes if you want to deploy something. And we, especially coming from industry, face this problem much more than, say, academic researchers, because for us, most of the time, our gold standard is to get it to deployments. So then, like these presentations by some, these blog articles here as well, it says, "Hey, my data scientist can't write production code," right? And it sounds kind of a criticism of data scientists, but that is actually not what I'm trying to point out. It is not expected for data scientists to know how to write production code. So a production code requires a lot of different skill sets, and I'm not going to go over all of these just in the interest of time, but just to highlight this thing, none of the above skill sets are required to include a strong competency in production software development, right? So the strengths of a data scientist are usually not the strengths of a person who produces production level software, and vice versa, right? They each have their unique strengths, and they don't usually intersect. So this is like the typical mess. Many of you who are in have used production level software or are involved in developing production level software, especially in the data science area, will identify with this. So you might have streaming data sources, you might have IoT data sources. Oh, I need to go back up. Okay. IoT data sources, you might have web data sources, and they all through some message bus or some like Kafka like facility is sent to some data store, right? And from that data store, then you have your usual ETL logic, which is the um, extract, transform, load kind of logic. This can actually be a little bit more than ETL. And then finally, there is this training, right? And this training is where all the media attention, all the attention of a lot of people working in machine learning is primarily focused on, right? And so this is the ML perception part, the rightmost part on the slide, and the rest of it is what is kind of reality when you want to use this in real life scenarios and in production environments. And it keeps getting messier, right? Because people want to do certain things on private clouds, certain things on public clouds such as GCP, AWS. Then there are network differences, like campus is different versus branch is different, data center is different, edge is different. So like data can come from all sorts of places. Training needs to be done again. Different types of data leads to different types of training. And finally, the deployment or the serving of it is another thing that is usually seldom talked about, because model training and getting more and more accurate models is the more in thing and the more in fashion thing. Whereas once a model is trained, how you serve it at scale and what do you do to test out different kinds of models, like A/B testing and stuff like that. Those are usually not highlighted that much, right? So the summary of this, or the motivation of this work, is that operationalizing machine learning is not easy. I hope I have been able to convince you about that. So what do we do about it, right? So that's where the Kubeflow project comes in. Kubeflow is an open source project. So Kubeflow takes you from machine learning science to machine learning engineering in a multi-cloud world, right? So that's kind of the very high level definition of Kubeflow, but we'll go into a little bit more detail of Kubeflow, and that's all this tutorial is about. So the rest of my presentation will be carved out like this. So we have already talked a little bit about ML in production, so that part is done. I'll go into the Kubeflow basics, and then I'll go and in the third section I'll go into a subsection of Kubeflow called Katib, which is used for hyperparameter tuning. And then finally, I will try and conclude this presentation, after which we will immediately jump to the demo part of it by John. Okay? And as I said, before we move on to the demos, we can get into questions. And Jonu, in the meantime, if there are any urgent questions that you see, please interrupt me and I will try and answer it.
Sure.
I am right now looking only at the slides, so I'm not looking at the AirMeet tab. So anybody can visit Kubeflow. It's just kubeflow.org. Anyway, these slides, I'll try to make it shareable. On the repo itself, we'll share it, so you should be able to get access to it. So no need of making any screenshots or anything of that sort. So Kubeflow is an open source project dedicated to making deployments of machine learning workflows on Kubernetes simple, portable, and scalable, right? So here there are a few assumptions, or there is at least one major assumption, that this runs only on Kubernetes. Now, why only on Kubernetes? Because at the end of the day, a lot of these machine learning projects, they work on very large scale distributed systems, and there is no point in developing the distributed systems management part of it from the ground up again. So it is much easier to use Kubernetes, because that has kind of become the de facto way of managing distributed systems, whether that be on public clouds or on private distributed systems, or even on hybrid clouds, which is a combination of both private and public clouds. Kubeflow has a lot of contributors, and a lot of contributors and a lot of users as well. And this is not an up-to-date representation of which all companies have contributed and or are actively using the Kubeflow project. Right? So as you can see, of course, Cisco is there. Then a lot of other companies use and contribute to this, right? So Microsoft, NVIDIA, Selden is actually a kind of a plugin that works inside of Kubeflow already. And Aricto is a startup which works on Kubeflow. AWS has been interested in Kubeflow. So there's a lot of, the point here is that there is a lot of interest and active participation. So what are the features that Kubeflow provides, right? First of all, there is model training. That's the very basic thing that you need to do, both model training and model serving, right? These are the very basic services that it has to provide, and these were among the first ones that were developed in the community, right? There are a lot of other data science services, and these are, I would say, they are not very well flushed out, because different companies and different contributors have different kind of requirements, and so they each of them come and kind of add their own service and things like that, right? Then there is experiment tracking, as in how are your experiments running, if you have run the last 10 runs, which are doing better, which are doing worse, things like that. All those functionalities are inbuilt into Kubeflow. There's also model management, which is managing different versions of the models. And as I already alluded to in the agenda of the talk, there is hyperparameter tuning, which has become pretty important in most machine learning applications these days. And finally, workflow automation, which is basically kind of tying in all the pieces together so that everything stays automated and does not need to be manually done, or you don't need to do a part of the continue for the next with any kind of manual intervention. Uh, the Kubeflow architecture is, I mean, here this is not really a very detailed architecture, but just to give you a flavor of where in the kind of software stack or where in the stack does it lie. So at the very bottom is your infrastructure. It may be either cloud or on-prem, or it could just the infrastructure could just be your own laptop, right? You can do simple experiment on your own laptop as well. And then there are on top of it there are container runtimes, and on top of the container runtimes you have a container management system, which is Kubernetes, and on top of Kubernetes, usually you have your general applications for anything which is non-Kubeflow. But in this case, you have this layer called Kubeflow, right? And on the Kubeflow layer, you can run your ML workloads, right? Whatever features of Kubeflow you want to use. So it's basically a very simple kind of plugin architecture. In a sense, Kubeflow just comes and sits on top of Kubernetes. So all that Kubeflow expects from the southbound interface is a Kubernetes interface. So it does not care whether the Kubernetes is running on your laptop or on, say, AWS or on some private cloud. It just does not care. Right? So one of the quick ways of using, or one of the common ways of using Kubeflow is to run Kubeflow programs on your laptop, and then once you are happy with whatever data set and accuracy and results that you get on your laptop, then simply by changing the Kubernetes configuration, you can now run the same experiment from your laptop on, say, Google Cloud or AWS, right? Just by changing the Kubernetes configuration. So yeah, so this is kind of the stacked architecture of Kubeflow. This is a little busy slide. Again, you can take a look at it at your own leisure, but basically what it tries to say is that there are a few different layers of Kubeflow, and like libraries and CLIs, higher level services like Katib, which is your hyperparameter tuning, pipelines, which we'll go into, notebooks that we'll go into as well. And then there are some low level APIs which are used by all these high level services, right? And if a box is white, it means that it's a component that has been developed within the Kubeflow ecosystem. Whereas if it's a different color, I guess it's purple or something. If it's that color box, then it has been developed outside of Kubeflow. So as you can see, most of them have been developed within the Kubeflow ecosystem, whereas a few of them, such as Argo, is from outside. Selden is by the company Selden, but they also integrate with us, as well as Spark, which is not native to Kubeflow, or which is not developed by Kubeflow. So what are the Kubeflow constructs, right? So if we go into the constructs, when I mean construct, these are kind of the terms that you'll hear inside Kubeflow when you want to do certain things. So there are operators, which we will go into the details of this. Operators, notebooks, pipelines, serving, and finally Katib. These are not the only construct. These are the constructs that we are presenting here, and among the most important constructs that are available within Kubeflow. So what are operators? Operators, nothing but they provide a set of uh, Kubernetes custom resources that turns distributed concepts in ML frameworks into Kubernetes resources. So if you are not familiar with Kubernetes too much, then some of these might sound a little bit alien to you, but this is basically allowing you to easily configure and run local or distributed training jobs of various ML frameworks on Kubernetes. For example, you could use TensorFlow, you could use PyTorch. So each of them, so TensorFlow has a particular operator, PyTorch would have another operator, and the Kubeflow architecture is extensible enough that if you have any specific or unique operator or unique what should I say, framework, you can always write an operator, and that would allow you to run your programs written in your framework to run on Kubeflow. Then there is the concept of notebooks, which is basically I think everybody in data science knows. These are Jupyter notebooks. So there are notebook servers within Kubeflow where you can run your Jupyter notebooks and where you can code up whatever you want to code up, and then test it out, things like that. And from there itself, you can start deploying it as containers on Kubernetes, right? So basically, very quick way of testing, writing, like scribbling down whatever you want to write, and then from slowly from there you start developing. It's almost an, what should I say, it's a ID, right? A developer environment, which can start from something very simple and then can use all the Kubeflow constructs to make the experiment or the thing production grade and running on large scale clusters as well, right? One of the most important constructs of Kubeflow is pipelines, which is nothing but it's basically combines individual tasks into end-to-end workflow. So you can develop individual components which are like think of them as function calls, something like that, and then you can tie these together in any manner that you want, and then this is what runs basically, right? When you start a run, then this is what runs, right? So for example, here there is a I mean, it's just some random example. So some generators, some then validators, then transform. You finally have a trainer and things like that, right? So it's basically whatever the data scientist decides are the important components of the program that he or she wants to write. So this also enables components and importantly sharing. So you can use the same component in some other workflow. So somebody else can use a block that somebody else has developed, right? And it helps with job tracking, experimentation, monitoring. We'll see later as well. I think John is going to show examples of pipelines. Right? So these were the very what would I say, the very basic constructs of Kubeflow. And now I'm going to move on to a little bit further description of Katib, which is the hyperparameter tuning. I am going to go a little fast on the first parts of Katib because that's on hyperparameter tuning, and I think this community already understands what hyperparameter tuning is, but I'm just going to go over it quickly so that for completeness, in case somebody is new to this concept, he or she should not miss out on understanding it. So hyperparameters are parameters external to the model and are fixed before the training process. So you cannot modify that during training. You cannot learn them during training, right? Examples are learning rate, batch size, number of epochs, momentum, things like that, right? Hyperparameter tuning finds values for these hyperparameters so that before you run a full-scale training job, you have a fair idea of what hyperparameters should this be used. Because if you use a very bad hyperparameter, you would be running, you would be doing a training process which would not give you the best results, and you would have to come and tune those hyperparameters. Earlier, that used to be done manually. Now there is hyperparameter tuning is a meta learning task, so which can also be automated, right? So why is HP tuning hard? Why do we want it to be automated? Obviously, its manual tuning is inefficient and error prone, especially for large training sets or training that takes a long time. And if the hyperparameters increase, then the search space becomes exponential, and you have to track multiple different hyperparameters across different training jobs, and it just becomes very difficult, right? And there is a variety of frameworks and algorithms for hyperparameter tuning. So if somebody is doing it manually, then you have to pick and choose which tuner you have to use, and then should you try a new tuner again, that becomes a impediment in speeding up your training process. So Katib is the hyperparameter tuner in Kubeflow, right? So what Katib, the main features of Katib worth highlighting here are that it is framework agnostic. So it will work for TensorFlow jobs, PyTorch jobs, MXNet, and basically anything that has an underlying operator, right? And the other good thing is that it has a customizable hyperparameter tuning algorithm backend, which means that it comes with a few standard search hyperparameter tuning algorithms like random search, grid search, Bayesian optimization, and hyperband. And I think by now there might be a few more that have already come in. And it also allows you to write your own. I mean, you can always write a piece of code and plug in that as the HP tuner, because you might have a very specific use case for which you know exactly what hyperparameter tuner to use, and so you can write that up as well. So I'm not going to go into too much detail into this. Again, the slides will be available. So what happens is in a hyperparameter tuner is that you basically, and I think this community knows about it, is that you create an experiment and then you send this to an experiment controller, which then requests a suggestion controller, which comes up with certain suggestions of the hyperparameters. The suggestions go back to the experiment controller. That kind of completes the definition of trial, and that goes to the trial controller, which runs multiple trials, and then the results from this are again fed back to the experiment controller, which then uses that to ask the suggestion controller for the next set of suggestion, and the process goes on and on um, till like while not experiment objective reached, like while till the experiment objective is reached, or some sort of timeout or something you can put, right? So it's just a while loop which kinds of tries to fine tune after every step. It's basically very similar to what usual machine learning training also does, which is repeatedly go over with slight modifications here and there. So I'm basically at the end of this presentation. So I'm going to make a few, concluding remarks about Kubeflow, and then, as I said, we will pause a little bit for question answers, and then we'll move to the demo. So, in conclusion, hopefully, I have been able to convince you that production machine learning is non-trivial. It is not easy to move from a data science project to a and Kubeflow is exactly developed for that. So Kubeflow is for machine learning lifecycle management, enables modeling, training, tuning, serving, monitoring, etc. And it basically simplifies the machine learning dev and ops. And Kubeflow runs on on-prem servers, software, and on the public cloud or hybrid cloud or whatever. As long as you have a Kubernetes endpoint, you can run Kubeflow. That's the way to look at it. Just for completeness, I have some action items for people who are interested. You can always visit kubeflow.org, but more importantly, this link is where we have put the entire code that John is going to demonstrate next. Is available on GitHub. This is open to everybody. You can take a look at that. You can fork it, copy it, and if you have questions, you can also ask there itself in the issues after this tutorial, so that even after this tutorial is over, we do have a channel open for communication with us. Okay, thank you. Let me see if there are any questions at this point. I don't see any questions on the tab, so Janu, you can possibly
Yeah.
take over. I will stop
Yes.
sharing.
Yeah. Can see my screen, right? Right. Hi everyone. I'm Jono from Nutanix. I'll go through the demo. So before that, just to introduce, we have been active in Kubeflow community for pretty long time, and currently leading multiple working groups in Kubeflow, particularly training and AutoML working groups in Kubeflow. So given the background of Kubeflow, so in one liner, it basically aims at Kubernetes native deployment of ML workloads, right? Like while taking advantages of the core infra Kubernetes, primarily your scale and portability, while still able to configure all the manifest through a declarative management, like how other Kubernetes objects are done. So yeah. So here, for the purpose of demo, I have actually created a full-blown Kubeflow cluster on the Amazon Kubernetes engine, EKS, and the instructions, Kubeflow installations, you can actually see that in kubeflow.org page. There are multiple official guides by almost all platforms. You could just have a look at that if you have any questions. regarding the installation. And what I'm talking about is actually valid for any Kubernetes cluster, whether you are actually using AWS or in public cloud or on-premise private cloud. So here what I have seen is I've created a default Kubeflow installation, and by default, all the Kubeflow core components are installed on the Kubeflow namespace, and you could see multiple services. And these services, just to highlight, these services are totally independent and they do not depend on the other. So basically, you could actually deploy just one service based on your use case and leave the rest, while the default one actually installs everything together. That is one key difference. And the default installation gets a multi-user mode, which means that each user can access any of this component independently and is isolated from the other user. So one cannot see the usage actually from the other user. So there is a isolation which is happening, user isolation, which is happening through namespaces in Kubeflow. So which means that every user basically gets a particular namespace when he is creating a login in Kubeflow multi-user mode. So here I have a general user at example.com as the username. And I can act only in my assigned namespace, which is Kubeflow user example.com. While when a new user registers and logs in, he will get a different namespace. He can use the core Kubeflow namespace, while he cannot access the other user namespaces. So I'll just go through the different microservices which are there in the default Kubeflow installation. So there are lots of microservices which are installed that like brief idea Amit has already talked about. So there is a central dashboard which basically creates the UI handling the user interface. There's a Jupyter microservice which creates the Jupyter notebooks for users. There is Katib, which takes care of your hyperparameter tuning and in general AutoML domain. I'll talk more about it later. Cave serving component, which handles model serving in Kubeflow. These are core Kubeflow components, right? Metadata services which take care of your metadata storage of your experiments. Um, uh, then there is training operator, which takes care of model training. Um, and it supports, Amit has already talked about, it supports almost all training frameworks, right? Like say, whether it is TensorFlow, PyTorch, MXNet, and XGBoost, all works in the same training operator microservice. So in the current release, MPI operator is kept separate, where you can run MPI jobs. And in the upcoming releases, it will be merged onto the training operator itself. And above all, there is a Kubeflow pipeline component, which basically stitches all these components into a single ML workflow. So you could think that as a single ML workflow which produces consistent and reproducible results in any Kubernetes cluster that you run. So this is like one way to have a reproducible workflow in your user premises based on your use case. So here so what I have thought is I'll take a very simple ML model. We are not focusing on the complexity of ML model, but we are like in this demo, we are focusing on the process from a simple model which is created by data scientists, go through the software life cycle and get your model onto the production. So what is the process involved in that, right? So here, what I have done is I've taken the standard time series anomaly detection ML model in the Keras website, which is using the convolutional autoencoder. So it's pretty much neatly described here, having artificially created time series, which is trained on the data which is labeled anomalous or not. And finally, when we are testing it, we provide a data which has anomaly, and then the idea is to predict whether if there is a sudden jump in data which is treated as anomaly. So that is the pretty much idea there. um, so we will take this as the ML model that we can rely on the subsequent configurations, right? Just to start, let's think about this use case, right? So a data scientist basically creates ML model, and he wants to actually put that into production. So what is the process involved there? So he might basically code that in a simple Python file, or he could basically use notebooks. So both are actually supported in Kubeflow domain. So let's take a simple use case where he starts with a Python file, and what can we do on top of it, right? So what I have done is, um, this is there in the GitHub as well. So if you want to refer that, you can take a look at that. So I have put all the ML code in anomaly train.py, which is exactly what you have seen in the website, right? Like there is no difference. And what I have done is towards the end, once model is trained, it is using standard Keras model, convolutional model, and then it is calling model.fit to train the model. And I have added model save to save the model. And if a S3 bucket option is given, I'll just upload that to S3. So that is pretty much exactly same from what you have seen in the Keras website. So at some point, when he has written the training code, he finds out that yeah, it works in his local laptop, but when he wants to do that in a scalable manner, he cannot basically rely on his local laptop. He needs more compute and advanced compute devices like say GPUs or TPUs or FPGAs, right? So how can he do that? And that is where Kubeflow comes into picture. So what Kubeflow provides is a set of operator constructs that Amit has already talked about. Here, we have to just write Kubernetes constructs in order to provide the distributed training. So here, the kind is TF job, which says I'm going to use a TensorFlow job. And this is pretty much same for other operators. Say if you have a PyTorch job, you have to just say PyTorch job. If it is XGBoost job, and it goes on, right? So the only thing that you have to do is you have to build an image, which is basically like a Kubernetes requirement from your the anomaly train.py, and you have to create a Docker image and then provide the command to run that. And once you do that, the Kubeflow training operator automatically provides the required the training distributed training constructs automatically for you, which basically makes it which makes the training distributed depending on the number of workers which he has specified. So in this example, you could see that I have 3 replicas configured, right? So automatically, what the training operator does is your single machine anomaly train.py is basically made distributed, and it is run on 3 different machines. And there are extra configurations which you can provide if you want scheduling, different types of scheduling. But in general, it will be run in 3 different pods. And here I'm using the worker type as the replica type, and there are multiple types in TensorFlow if you want. These are extra confidence which you provide, but in general, you could say what are the number of replicas that I need, and you provide the image. So it automatically creates a construct for you. And the cool thing is, in the same configuration, you could provide whether I need GPUs, what is the CPU requirement that I need, what is the memory requirement that I need for the training job, and it automatically creates that for you. So in this case, each replica would basically use 2 GPUs, and which automatically says I will have altogether for my training job, I will have 6 GPUs used running in 3 pods, and you'll get the results back as a distributed result. So there are many configurations possible. Say like, what should I do with the pods once the job is complete? if a failure happens, what should I do? Whether should I restart the job? What is the backup limit when there are multiple failures? What should I do? There are lots of extra configurations that you can actually make up on top of that. So just to show what happens, I have since it takes time, I have already run it. Um, so I already have created a training job, and so there were 3 pods, and you could see that the anomaly train.worker 012 was started and it got completed, and the status of the entire job was actually succeeded. um, with the 3 workers succeeded, right? And end of it, I would have actually created a train model, which is, and if I've created option to save the model, I would have actually saved in some location, either in the local cluster or somewhere outside. Like in the current code, I have actually added to save the model in the S3 storage. And just to highlight, if you are doing the same thing in Kubeflow cluster, there is an option to do that in cluster, which is using a component called fairing, which automatically build a Docker image and deploy a TF job or PyTorch job for you inside the Kubeflow cluster. So you could write simple ML code inside the notebook cluster, use pairing to deploy the notebook code onto a let's say if it is a AWS or a GCP, or if it is Azure, you could automatically deploy directly within the notebook using a component called pairing. So if you have any questions, Amit, please interrupt me so that I'll.
Jonu, there is one question. The automatic annotation functionality of a notebook cell by Arictos Rock are okay, and taking snapshots from the Jupyter notebook to create a pipeline. Is this construct added in native Kubeflow with new version currently?
It is yet to be added. It is not there in the default Kubeflow installation. So here we have talked about training the ML model, right? So we have a train model. Now let's talk about how we can tune that. And Amit has already talked about using component called Katib. So Katib deals with the auto ML domain in general. So currently it looks at majorly 2 areas. One is your hyperparameter tuning, which is tuning of hyperparameters associated with the model. The second one is the network architecture search, which is NAS class, where if you are using neural network architectures, you could basically use Katib to figure out what is the best architecture suited for my use case. So these are the main 2 class of algorithms that are actually presently used in Katib, and it is fully homegrown within the Kubeflow. And there are multiple algorithms in case of hyperparameter tuning. We have random grid, hyperband, Bayesian, and many more algorithms. And in case of NAS, we have ENAS and DARTs, which is actually there in upstream. And people are actually using custom algorithms in their premises as well, which is another key advantage of Katib, where they can plug in custom algorithms if they actually need to without even restarting your job. So when it comes to tuning, so here I have taken the exactly same the anomaly train, and the only change that I have actually added, I have identified what are the hyperparameters that I have to change, right? Here, the hyperparameters that I have to tune, I have added to be the learning rate and um, the batch size. So the only difference is earlier I have hard coded that it was 128 earlier. Here when you are doing with Katib, you have to just pass this argument as a command line argument when you are invoking this. That's the only change. Rest all the training code remains exactly same. So here, if you see that in the first part, These are two extra command line arguments that have to be added. And in order to write your Katib experiment, it is again a pretty much advanced hyperparameter tune system with lots of configuration. I'll just give a very brief idea how it works. So you have to basically write a Katib experiment through your Kubernetes config, right? So here there are majorly four sections. So first section is objective, which basically says what is the objective of my hyperparameter tuning process. So here I'm saying I'm going to minimize the objective metric name called loss function to reach the final goal of 0.01. And I have to also track the validation loss. So these are the metrics which are emitted by your training container, right? Like when you are running a Keras model fit, you would basically say what is the metric that you are interested in. So these are the two metrics that are emitted from your training container. And regarding the algorithm, I'm going to use grid algorithm. Um, in order to restrict the total compute usage, you could basically say max trial count. So if you are not specifying that, it will run infinitely. So here I'm going to run maximum of 10 trials, and 3 trials can run in parallel. And if there are 3 failed trials, I'll say that my experiment has failed. So this is like the final the upper limit for maximum failed trial jobs. In the next section, I'm saying what are the parameters that I have to tune. So here I have 2 parameters, which is learning rate and batch size, and I have to provide the feasible space that I'm interested in to optimize. So here the minimum is 0.01, the maximum is 0.01, and the step size is also specified, and same is the case with batch size. So for example, here batch, there will be 64, 128, 192, and 256 as the maximum are the possible values that can be added for batch size.
Janu, there is a question.
Yeah.
So what is meant by a failed trial?
So say for example, you have provided a training container, and the training container for some reason fails, right? It's not actually part of Katib, but again, say you have some segmentation fault or some other condition which made your training container fail. So the problem is if you are not handling that, there will be too many failures, and it will actually use some of the compute resources in your Kubernetes cluster, right? Because it will keep on spawning new pods, new trials in order to make it succeeded. So here we have just put a maximum trial count for fail, so that your compute resources, even for your failed limits, are satisfied.
So it would also kick in situations like suppose the trial job wants 5 GPUs, but you don't have 5 GPUs
Exactly.
to allocate at all, right? So it will keep
Exactly.
on failing, right?
Exactly.
There
Uh,
is
so
another question, Janu. There is another question while we're at it. Would config specs like TF replica workers, etc., also apply to multi-agent RL libraries like Ray on Kubeflow? Ray has a separate comprehensive training config, so was curious how they would both work together.
So yeah, I think there's a proposal for that. Right now, we haven't integrated. So there's a separate proposal for integrating that with the Qflow components. I will, if I have time, I can basically give you that GitHub issue. It is being tracked in one GitHub issue.
Okay, let's go ahead.
Yeah. So in other words, your experiment will get succeeded in these conditions, right? One, your objective metric is met, right? Like your loss function has come to 0.01, your experiment gets succeeded. One. Second, it hasn't met, but you have run maximum trials, right? Like say you have run 10 trials, and that's all I want to run, so it gets succeeded. Third, I have max of 3 failed trials, and when I see that there are 3 failed trials, I'll say my experiment got completed, but it is in failed state. Earlier it wasn't succeeded, right? In the other condition it was succeeded. And the final section is actually the trial template, and that is where you have to provide your training container which you want to tune, right? And I have told that I have modified the anomaly tune.py to accept the command line arguments, right? So here the only thing that you have to do is um, anomaly tune.py, your training container that you have to tune, you have to basically accept command line parameters, and you have to add that in your command when you are actually specifying a training container. That's all what you have to do. And your Katib controller in each iteration will create a set of hyperparameter values and pass on to your training container, substituting the right values, right? Like you don't need to worry about it. So I think it will get more clear when you see how this is done. So I have run this, and so this is in succeeded state. Let's see what has happened, right? So in the state, so here I have had max of 10 trials, and I have done all the 10 trials, right? And it is in succeeded state. These are the 10 trials which are run, and each trial corresponds to one set of hyperparameters, right? Like it will have one set of LR, learning rate, and one value for batch size. And it basically says my best trial is this, with the parameter assignment LR as 0.04 and batch size as 64, and the corresponding value for loss function is 0.028, and the validation loss is 0.017. So we are tracking the other values also for accounting purposes, but since it's a minimization function, we are interested in the min value here. So the loss function, the best loss function which we have got is 0.028, and you could see that the goal was 0.01. That is why it kept on running till your max trial count has reached, right? And so here you could see that experiment has succeeded because the max trial count has reached. So there are many ways to debug. If you are interested in deep diving, you could basically get all the trials which are run, what are the corresponding values to each of them, etc., etc. And if you want to even restart the same experiment, you could basically say, currently I have run 10 trials. Let me resume the same experiment with extra 15 more trials, right? Like when I have more compute resources, I'll just extend this experiment to more trials. You could just change number of trials, and experiment will start kicking in from the last point, and it will run for the extra number of trials. So I just want to show the UI as well for this.
Janu, before you move to that, there is another question. Do we need to provide the range of the hyperparameters?
Yes. So that basically restricts your hyperparameter space. So what typically like people do is, so initially you will keep larger spaces, right? And then once you get a basic idea where your best optimized value lies, then and you will run for lesser number of trials, and you will basically reduce that space to a better range with more number of trials. That's what it does. And that is what like there are advanced like say basically hyperband and Bayesian optimization automatically takes care of it. They does exactly same, right? Like they basically half the feasible space each time when they actually do that. So you don't need to worry too much about how this is done, because there are many black box optimization algorithms which actually does it in a very good. We can try some of these algorithms, and you'll be surprised how you basically get best values out of that. So here there's a UI as well for the hyperparameter tuning. Like if you are interested in how things actually worked. Um, yeah. So here, as I've said, my best loss function was 0.028, and I have the corresponding val loss and the parameters associated with that. So in the UI, there's a very nice figure to basically understand how this is being converged, right? And this figure basically explains the importance of hyperparameter tuning, right? So if you can see that your loss function, the loss value that you have received basically ranged from 0.02 to 0.003, which is basically 100 times, yeah, 10 times difference, right? And each one shows what is the corresponding value that I have taken for what is the corresponding LR and batch size, which made this particular loss function to get to this value. So for example, 0.03, what are the value that I have actually got? 0.028, actually it hasn't reached 0. Right. So here there are more details. Experiment has succeeded because the max trial count has reached. It basically says about the trial params, trial best performance. It also talks about the various trials that I have run and the corresponding loss and val function. So if you are just interested in the UI part, not command line provides more configurations and more details about the results. This is like a condensed view of what you are seeing in the command line, and more details are here as well. So this is about the tuning part. Now, so where did we reach, right? So we have trained a model, we have tuned a model with the right set of parameters, right? And we have almost reached the goal that we are planning to be there, right? Like we have reached around 0.02, and if I'm sure, like if you're running for more trials, we'll get a better result here. And at the end of it, we save this optimized model somewhere. Now let's go to the model serving part. So just to give a heads up, so here we could use your the serving component in Kubeflow, which is called the KF serving, and that takes very simple configuration. You should just point to the model that you have created. It can be in S3, it can be in on cluster volumes, or it can be in GCS or Azure, and you have to just say what framework that you are going to use. So here I'm using TensorFlow, and when you apply that, what happens is it will use the official serving frameworks corresponding to that. So if it is a TensorFlow, it uses official TF serving container to serve the TensorFlow model that you have created. If it is PyTorch serve, and for other custom containers, there is a custom serving container which is created within KF serving. But just in order to show the hybrid workflow deployment and the true power of Kubeflow, what I have done is I'm basically using the train model to run on the AWS SageMaker. So tomorrow you could basically run training on-prem or in any other public cloud, and you could basically serve on a cloud service, and that needn't be even AWS SageMaker, right? Like it can be in GCP as well, or it can be in cluster as well. So I'm just, in order to show the true the hybrid nature of Kubeflow, I've just done a deployment in AWS SageMaker. So here I have just added a simple script which basically creates a Docker of the serving code, and I have pushed it to the AWS SageMaker. So for AWS SageMaker, the only requirement is you have to basically create container. You have to create a container with two APIs, and this is a requirement from AWS SageMaker, which is /ping and /invocations. So /ping basically has to provide 200 when the service is up, and invocation basically provides for the prediction output for the input that it is received. And this is the requirement from the SageMaker, which is built on simple Flask API. So we have like if you have seen that, we have trained, tuned, and our serving containers are ready, right? So here we have done all through manual steps, right? Like people who are comfortable with the manual way of deployment, he could basically do it in a single command line argument. He could do a deployment of training, Katib tuning, and the serving, right? Like Kubernetes create one config file. That's what it is required. Now, I just want to talk about the final component, which is called Kubeflow pipelines, right?
Janu, before we move on to that, there are two more questions. Does Katib optimize the additional metrics, val like loss, or the actual metrics loss, or a combination of both?
So right now we have just a single metric optimization. The other metrics are just tracked, right? So when we are saying go and optimize loss function, uh, other metrics are tracked, and we would be able to understand what is the value of the other metrics during that time, but it is not optimized. It is a single metric optimization here. So if you are interested in optimizing val loss, keep that as a objective metric name, and if you want to track loss as well, then add that as the additional metric name. But you could just do optimize of just one metric.
The other question is, how does NAS work on Kubeflow?
So there is a separate configuration similar to what we have seen for HTTP tuning. There is a NAS config. I haven't actually provided that. It is in beta stage. You have to provide what are the maximum number of layers allowed, what are the maximum number of nodes allowed in each of the layers, etc. So there's a NAS config which can be provided in the same experiment that you have seen.
Okay, go ahead. No more questions
Yeah.
at this point.
Sounds good. So basically, this is here the central dashboard, Kubeflow central dashboard. I'll just talk about what it is here as well. So here you could basically create a new notebook if you are interested. So one difference from the normal notebook and the Kubeflow notebook would be it is tightly integrated with other Kubeflow components, right? Like say, for example, if you want to access Kubeflow pipelines within notebook, you don't need any extra configurations. You could actually use in cluster service within notebook directly without any authentication. You could basically use similarly, you could use Katib, you could start deploying stuff within notebook, etc. There are lots of assets. In the earlier slide I've talked about fairing, right? Like which you could basically build and deploy stuff within Kubeflow notebook without any extra configurations. So even within the notebook as well, there are some advanced configurations where you could provide what image should I use, what is the CPU requirements, RAM requirements, whether if I have GPUs in the cluster, I can attach GPUs to notebooks, etc. Persistent, if I need to have persistent storage attached to the notebook, or if I need to set some extra configurations or environment variables, I can do that as well. Attention. This is a model serving part. I have already talked about the AutoML part, the Katib, and the last part is actually the KFP, which is Kubeflow pipelines. So there are two ways to create Kubeflow pipelines. One,
Janu, sorry to interrupt. Just a quick time check. We have around 25 minutes left.
Sure. So there are two ways to create a Kubeflow experience. One is actually through UI, where user can manually create the pipeline config and upload it. Everything through UI. That is one way to do it. The other way, he could basically use pipeline SDK to create that entire ML workflow, and then even create an experiment and start executing that all within the pipeline SDK. So that is what I'm planning to do. So there is no manual stuff here. So I have actually created a notebook here, and here what you are basically seeing here, it's exactly same prediction code from Kera's website. I have actually put that onto uh, the notebook here. So it's the same thing here. You have the training data, etc. So Now this is the key area that you are going to use with the pipeline SDK. So you have to basically create multiple steps in pipeline, right? So the first step is basically creating the training upload, the training container. So there is a pipeline SDK to create a container step. So I'm going to use the anomaly train um, container, and I'm passing the S3 bucket, and this is the first step here. And you have to basically stitch the entire process through the SDK. So if you see here, you have a training step here. I am creating, so this training step uploads your train model onto the S3. Now I am, second step is the SageMaker model op, which basically creates a model in SageMaker after that the training one. Now the final step is deploying that SageMaker endpoint, and then and that is done after the create model step, which is creating. So this is the one which is creating that lineage of what steps are executed at what time. And I'm creating the pipeline workflow, which creates the experiment, and then I'm creating the run, right? And once I create the run, I'm constantly seeing what is the status of the endpoint all through the SageMaker one. So if you go to the experiment that actually got created, right? This is the experiment that actually got created here through notebook. So these are steps which I the lineage of steps that I have already talked about. So I have mounted a log volume. The training is actually done here. Like it is the same, exactly same training step. Now there's no difference. At the end of it, it is uploaded to S3. There are lots of options here. Once you deploy that, I think you'll get a better idea. I recommend to try it on your own. So you create a model in SageMaker and deploy it, right? And you could basically see that all things happen in AWS in real time. The SageMaker endpoint is actually created, and it is in service. So once it is in service, you could now you are ready to do predictions on top of that. So I'm basically using the prediction endpoint, which is in service, and using that to do the final prediction. So this is the prediction, the prediction URL endpoint, which is getting called to get the prediction value, and that is constructed to see that I've detected an anomaly at this point. So like uh, to reiterate, what has happened is through pipeline SDK, I have created the entire ML workflow, and this can be triggered directly from notebook, or it can be even triggered from external and sources as well. Say for example, in your use cases, when there's a push to GitHub, go and trigger a particular ML workflow, pipeline workflow. That is possible. Or it can be, say, some message in Kafka, right? Once you get a message, go and trigger a ML workflow. That is possible through the KFP, Kubeflow pipelines. And once that is triggered, it basically executes from your source to destination. And you could actually add in one of the slides that Amit showed, you're seeing there are multiple possibilities, right? You could basically check some condition. If this is true, then go and redeploy it. All these things can be done. Say you have got new data coming in. If it is something interesting, then go and retrain the model. So all these conditions can be added within the ML workflow to trigger the final model deployment and change the model if required. Any other questions?
There is one. I have also created a poll that might have gone online right now. I will check the question as well. Question is, how does, okay, I'll go sequentially, the earliest first. Since Kubernetes scheduling functionality are not specifically designed to do deep learning training, resulting many problems during the scheduling process of deploying distributed jobs on Kubernetes, is there any dynamic resource scheduler?
Yeah, it's a very good question. So in the training, if you see the training operator, there is a feature called gang scheduling, and you could provide any open source or even closed source gang scheduler as an extra argument. You could check out that, which is, and the term is called gang scheduling. And right now, as default, we are using Volcano. And what it does is it has all these extra scheduling options that you have already asked. Say, for example, if I have X machines together, then only I will start deep learning. Else, I'll just wait for these many number of machines to come up, etc. But by default, Kubernetes will start scheduling it, right? Which is not the right way to do for a deep learning job. So all these extra options are possible through machine learning specific schedulers, and Volcano is one example that we constantly use. You can check out that, and the term is called gang scheduling.
Next is it possible to provide multiple loss functions so that all can be optimized for simultaneously?
Yeah, that is in works. From most likely, it will be in one of the upcoming releases. And there's a GitHub issue as well in Katib repository tracking that. If you are interested, please check out that.
Any plan in Kubeflow in future release for doing distributed deep learning?
That's exactly what it is done by the training operator. Say, for example, you can basically do a single node training, or you can do a distributed training by just changing the number of replicas, and you could even specify strategies as well. In the upcoming release, um, the PyTorch job will actually support. I'm just giving an example. It will support elastic training as well. Say, like you could basically change number of machines on the fly, which will basically scale up and down your training job. So there are multiple strategies also are supported. Say, if you are interested in all reduce, you could use certain configurations. If you are interested in parameter server strategies, you could use certain configurations. So there are advanced configuration strategies supported in the training operator at present.
The next question is, does Kubeflow also support model monitoring for drifts in production?
Currently, it is not there. Earlier, the efforts was there in the Kubeflow community. Unfortunately, it is not continuously monitored right now. So you can just check it, the metadata project. Right now, people are mostly using the MLMD, Google ML metadata project for tracking the experiment as well. But there was a separate metadata project, metadata repo itself in Kubeflow repository, but that is not actively developed now.
So in that case, it is possible to use the Google project to monitor the results and then trigger Kubeflow pipelines?
Yes,
Right?
yes, yeah.
The last question as of now is, other than SageMaker, what other options are available for model creation and deployment?
So this was just an example. So I was just trying to prove the hybrid nature here. So what we have done is we have trained in cluster, in a Kubernetes cluster. So that means today it can be in AWS, it can be tomorrow, it can be in an on-premise cluster, right? Private cluster. I can train, and I can even deploy within the same cluster using KF serving, or I can basically use any other cloud service to deploy it, right? Like it can be in GCP, it can be in AWS, and most of the services have a Kubeflow pipeline component. So, like if you have seen in my notebook, I have basically used the official SageMaker component here. SageMaker model op and SageMaker deploy operations are official SageMaker components for Kubeflow pipelines. So for GCP as well, I'm sure that there are uh, pipeline components which can deploy a model to the GCP component. So you are free to use in either way. And there's a separate KF serving component as well within the pipeline, where the model will be served using KF serving within the cluster.
Before I move on to the next question, I would on your screen you will see on the a poll. So if you can, while you're listening to it, it's a quick poll, so you can answer it as well. And in the meantime, I will move on to the next question. Okay. So it should be available on the poll tab, I believe. There is another question. Okay, please, could you help me in choosing Kubeflow versus MLflow? I was expecting this question.
It's a tough call. So one key difference that is MLflow is a like it's a very popular open source tool. It's good for open source, but again, when you want to put that into production, it is tough, right? Because it doesn't have authentication by default. It doesn't have um, uh, uh, that scalable thing by default. You could plug in that for sure, but again, there is extra effort there. So
So
I
let me answer that question with an example. Like in within Cisco, we are actually using Kubeflow, and so the team that is trying to use Kubeflow, they also like certain features of MLflow. So what has happened is that in the underlying distribution that we have, it is a combination of both Kubeflow and MLflow. They are using certain features of MLflow, but they are mostly using Kubeflow. So yeah, it is.
and to highlight, they have a metadata tracking
Yeah.
server, which is actually not there in Kubeflow. I'm saying
Yes.
so. I know many users who are actually using MLflow's metadata tracking server, which has a very nice UI and an API to push metrics and other stuff to a metadata server, which is actually to the one of the questions that was asked earlier, right?
Yeah.
People actually use MLflow for that.
So so basically, the question is not an either or, but it is you can use a combination of this. Most people seem to use MLflow for a very specific use case, and a lot of the other use cases are being covered by Q. Jonu, are you done with your presentation?
Yes.
Okay. So we don't see any further questions at this point. We can wait a couple more minutes, and then if there are no more questions, then we can go ahead and end the tutorial.
Okay, Amit, I don't see any further questions.
Yes.
Other participants, if you have any questions, you can post it now.
And as I mentioned earlier, the repo is also available. I posted the link on the chat, and the recording probably will be made available later. That's up to the tutorial chairs. So you can also ask questions on the repo in case you think of something later. I will be closing the poll right
Yeah.
now. So this is, if you wanted to vote on the poll, then this is kind of your last chance. I'll be closing it right now. So this is the current poll outcome. So 27 votes. With the question was whether this whole problem of moving from proof of concept to production grade deployment a realistic use case for this audience. So 27 people have voted. 10 or 37% say that it's very often a use case, and and for the rest it is sometimes use case. Interestingly, and I did expect this, but nobody has said that it is never the use case. So that's interesting. That's a good validation of our talk. Okay, we are done.
Yeah. Okay. Thanks, Amit. Thanks for this session. And John, it was very interactive and nice session. I hope the participants had a good session from all the things. So before we end the thing, just give us 2 minutes to 5 minutes for our sponsor video, who have helped us to run these COTS Command Conference. So we'll just play some video and a message from the sponsor, and then we will end the session. Okay. Thank you so much.
Thank
So
you.
Atul,
Thank you
over
for
to you.
hosting us.
My name is Ravi Balasubramanian. I'm a Director of Data Science at Walmart. I'm going to present on behalf of my broader data science and AI teams within the Walmart India Development Center. I shall talk about how data science and AI is driving digital transformation within Walmart. I will also highlight various application areas through some examples where our algorithms and solutions have been deployed to guide everyday decision making. AI is core to most of our products, and we are enabling solutions across the full retail value chain. On customer touchpoints, we have multiple segmentation algorithms to understand customer behavior and preferences, so we recommend the most relevant products to our customers. We work very closely with our merchants and third-party sellers on what they should sell in our e-com and stores, how they should price the products, and when they should run markdowns and promotions, and how should the product placement be in the stores and in e-com. With our supply chain planners and suppliers, we work with them on product attributes and inventory replenishment. So we carry just the right amount of inventory, not excess nor out of stock. On the operational side of things, we work with our logistics and transportation planners with multiple predictive metrics to enable short-term and long-term planning. More than 100 million people shop in Walmart in a given week, so we do generate quite a lot of data. There is a ton of work happening on our end on time series algorithms, specifically on forecasting and optimization to drive operational planning and decision making. Besides that, we do quite a lot of work on text, images, and speech. We are building a conversational AI product to enable smooth customer shopping experience. There's work we are doing on image-based out-of-stock detection. On the tech side, we are building algorithms for building the taxonomy and catalog for our e-commerce stores. The next couple of slides, I will touch upon example application areas in more detail. Fresh Sales Tools is an app that is built for our Sam's Club store managers and employees with their inventory planning. A cool feature of this application is its accessibility via handheld devices like iPad. It produces daily forecast right before their shifts for high footfall departments like bakery, dairy, meat, and seafood. Sales forecasting is a critical module of FST, and we have leveraged multiple ML and deep learning algorithms to provide these daily forecasts. It's also built on top of an MLOps framework for continuous monitoring of performance. This is an interesting but practical everyday problem for us. Smart Sub is an AI solution we have built to enable product substitutions post-purchase. Our online grocery orders are typically served out of live stores. So occasionally some of these items go out of stock. Now, do we fulfill the order with a personalized substitute that is acceptable to our customers? That's the open problem statement. Couple of challenges here, because when customer place orders, we ask them for preferences, but we cannot go and ask a preference substitute for every item to add to the cart. The other challenge is when we offer substitutes, we don't want to eat away on our price margin. The solution we have built is a deep learning based graph convolutional neural net. We have factored in personalized signals as well as cross-channel signals from our customer cohorts. To solve the aspect of price difference, we have also integrated a constraint optimization approach here. So this solution has been deployed live. We are enabling our store employees with better decision making with the substitutes and same time keeping our customers happy and engaged. So in an online store, image catalog is the only perceivable medium for our customers. It is extremely important to efficiently manage our image catalog, as good quality images in all orientations play a very critical role in making the customer experience great. And selecting the quality images and ordering of orientations manually is very tedious and prone to errors. Hence, there is a need for an automated solution. Here, what we have built is a two-step solution. The first step is a hierarchical framework where we classify the various orientation of the images using a convolutional neural net with transfer learning. We were able to hit a very high accuracy of 94% in this phase with mobile net pre-trained embeddings and multinomial logistic regression. As the second step in the process, we have eased the process of catalog management by automatically assessing image quality using no reference image quality assessment and structural similarity metrics. It's an interesting application where we are detecting out of stock situations in stores through computer vision. This problem has a couple of challenges because the machines need to understand factors like depth, contrast, gradients, change in intensity to classify something as a void or nothing exists in that space. To overcome these challenges, we have innovatively augmented data as limited data was available for training to begin with. We used CNN based models to actually detect these objects and voids. We are continuously recalibrating these models based on their observed performance. Walmart spends millions of dollars on creating and curating site assets for our.com every year. So these could be in the form of creative carousels, inspirational banners, like say photos, videos presented under different modules for our different campaigns, whether it's a fall campaign or a spring campaign or like a seasonal campaign. And one of the major tasks in site management is identifying the right set of items to include it in the landing destination for the kind of campaign we are running. Manual curation of these products is a month-long process for every campaign, and scale it up with the number of campaigns we run every year. There's a lot of labor involved with time and effort. What we have built is an automated solution driven through AI to help our curation teams with an AI assisted solution. Speaking is very natural to humans, and we have actually built a conversational AI platform to enable our shoppers to actually do a voice-based ordering across many devices like smart speakers, mobile phones, in-car assistants for a faster, easier and friction-free shopping experience. I think we call it like say Walmart voice order for online grocery. A customer can actually place orders through voice. They can actually book time slots for picking up items from a store. And the ultimate goal of the platform is just to enable a very seamless touch point for our customers to have with Walmart. A core aspect that is enabling a lot of this data science work is our inbuilt ML platform called Element. It enables a data scientist to perform the end-to-end workflow, starting from ingestion of data to pre-processing, the feature engineering, model training, deployment, and model productionization. Some of the best MLOps practices on model monitoring, like say data drift, concept drift detections, and then looking at a model retraining triggers, metric-based retrainings. All of that is actually being facilitated through this end-to-end ML platform. The platform abstracts from the user the entire infrastructure. The user can actually choose the cloud environment he wants to deploy. It can spin off on the compute and use it without too much of a hassle. And also it enables productionization of models and manage the life cycle of ML models in a much seamless way. With this, I will end my talk. Hope I gave you guys a quick showcase of some of the application areas in data science that our team is actually working on. And we are open to questions now. Thank you.
Okay, so the speaker from Walmart is not available in the session. At least I cannot see him joining. So Kala, over to you.
Yeah, sure. So I'll just take 1 minute to take a photo. As I said, this is a photo moment. So Amit and Johnny, give your best smiles. And Atul, would you like to just switch on your cameras if you want? Okay, I'll just take it out. Thank you so much. I think it was a nice session, and hope we'll see you in the other sessions as you participate. Yeah.
Thank you. Bye.
Bye.